Let's say there's been a nuclear catastrophe and you've managed to survive, and the local council comes along and they hand out everyone 100 metres of fencing, and they say to everyone, you've got to go and create a rectangular plot, and you've got to go and plant potatoes in that plot, and those potatoes will allow you to survive through next winter. So you want to make sure you go and you do it properly. So we've got down here 100 metres of fencing, so the fencing's in red here, so the fencing goes from point 0 here, for example. If we were to take it to there, we go from 0 to 20, so that's 20 metres, and it'd be 20 metres there, which is 40 metres, and then we'd have another 30 metres each side, so that would be another 60 metres plus 40 metres. So there's 100 metres of fencing round here, and this is your plot. But then you notice that whenever you change the shape of your plot, you actually change the area. So for example, you start off with a plot and you start with a plot that looks like that, and you notice that the area of that plot is only going to be 1, 2, 3, 4 of these blocks. And again, the perimeter here is still 100, so that's 10 and 10 and 40 and 40, which adds up to 100. So you notice that that area is a value of 4. But then whenever you make the plot this shape, you'll notice that we still get the 100 metres of fencing, but the area now has gone from 4 up to 6. And of course, whenever you go and make the plot this shape, you notice that it's still 6, and then it drops down to 4 again. And if you continue along, the area will tend towards 0. So you realise that in order to plant the most potatoes and able to survive through the winter, you're going to have to find the shape that will give you the largest area, because the largest area will allow you to plant the greater number of potatoes. So you're trying to find the length here and the breadth that will ensure that you've got the largest area. And this is a problem of optimization, and we're going to use our knowledge of differentiation in order to solve this problem. So let's start off by noting that as we change this value of x, so this is the x here and this is the y here, as we change the value of x, the value of the area changes. So I've just put the area here on the plot, so that's the area. So that's simply this length times this breadth. This is our x times y. So we can notice that whenever the x is equal to 0, the area is equal to 0. Whenever x increases, you see the area getting bigger and bigger, and at some point round about 600 it hits a maximum value, and then it starts to decrease again. And we're trying to find the value of x that ensures that the area is a maximum. So really what we want to do is we want to relate the length here, x, with the area. So we're looking for a function that relates the value of x to the area. So let's go ahead and we'll see how we're going to do that. So let's go ahead and we'll plot a function here, which is the area as a function of this distance x. So what we want to do is, if we move this along, you'll see in black there's an extra line appearing. So that extra line that we have appearing, that is the function, which is the area as a function of this distance x. So for example, at the moment x is 1.4, and that's given us an area of 68.04. So we go along to 1.4 and we come up and we put a dot there, which is our 68.04, and we go ahead and we do that for all the values of x until eventually we get this function here, which is the area as a function of this distance x. So let's zoom out a bit, because we know that this area is going to go up to around about 600 and above. So if we zoom out and get the scales a bit better so we can see it. Okay, so that's a bit better, you can see the size of the function there. So if we were to then increase this value of x, you'll see that value getting up, that's a 184 there, to 75 and so on and so forth, and you see it getting up, getting bigger and bigger and bigger. As you can see, somewhere round about 600 or somewhere above 600 it starts to slow down, and then somewhere around about 600 to 650 it turns round and it starts heading back down again, and you can see it heading back down again because the area here started to decrease, and eventually it head all the way down until eventually the area goes to 0. So this here is our function, which is the area as a function of this distance x, and we're going to have to work out what that function is. But before we go ahead and do all the mathematics, let's see if we can figure out a way of solving this using our differentiation. Now, a thing to note is that we know that the area is a maximum at this point up here. So what's special about this point here? Well, the special thing about this point here is it's the stationary value. That is, the gradient at this point is equal to 0. But we know from using differentiation, we have a way of creating another function from this, and that other function will tell us the rate of change of this function. So that other function we create is the function we get when we differentiate this. So if we differentiate this function, we're going to get another function, and the height of that other function is going to tell us the gradient at each point in this function. So we know the gradient is equal to 0, so if we were to differentiate this function, then the new function we get, whenever that is equal to 0, we'll have our value for x that will give us the maximum area. So let's go ahead and we'll differentiate this function just now graphically, and we'll see all this. So we differentiate this black function here, and we get this red function. And you can see that the red function here, the height of it tells you the gradient of the black function. So for example, the gradient of this black function at 0 is very large, it's positive. So this is the value here, it's a large positive value that the red function starts from. But as we increase the area, you can see that the gradient of this function gets less and less, until eventually, at this point up here, the gradient is 0. So this function here, which is just a differentiated function, it'll have a value of 0 there, and that point there, where it has a value of 0, that's going to be the x distance that will give you the maximum area. And we can see here that that x distance is exactly 25. So we have a method here of solving this problem. What we need to do is we need to write the area as a function of this value x. Then we have to differentiate it. When we differentiate it, if we set that differentiated function equal to 0, then the value here that we get at 0 will be the x value that will give you the maximum area. And then after you have this x value for the maximum area, then you can work out the other sides of your rectangle. So for example here, we know that that x value is going to be 25. Now if this is a rectangle, then, and we've only got 100 meters worth of fencing, we know that we're going to have a value of 25 in one side, so we're going to have 25 up the other side, so that's 50. So that means that the x distances as well are going to be 25 each. So it means that in order to, the solution to this is going to be a rectangle which is 25 by 25 by 25 by 25. That is, it has to be a square. So really what we're saying is the rectangle that's going to give you the maximum area is always going to be a square. So let's have a final look at this, and we'll see that we actually get the maximum area by making it a square. So if we make it 25, so that's the x value being 25, The y value is 25, this is 25 and that's 25, so we've got 100 all the way around, and we've got a square, and the maximum area is going to be 25 times 25, which is 625. And if I go just a little bit left of that, you'll see it decreases. If I go a little bit right of that, you'll see it decreases. So you know, whenever you go and create your plot in order to plant your potatoes, you have to make it a square in order to make sure that you plant enough potatoes so you don't starve through winter. But of course, during the nuclear holocaust, all the computers have been wiped out as well, and you don't have a computer in order to solve it the way that we've solved it here. You have to do it with a pen and a piece of paper and using some differentiation and just using the knowledge that you have. So let's go ahead and we'll solve it like that.